for this week. I've prepared a few slides that I want to share with you, just to put into perspective the the exciting situation that we are in, and just to set the stage for the conversations of this week. We've been doing this conference now for 6 years. This is the 6th edition, and when we started, honestly, storage was a important but relatively small aspect of the solar industry. And in just 6 years' time, it has really completely changed. And it is reshaping the entire industry, reshaping how people get access and consume electricity in Africa. And these are very, very exciting times. If you look at the evolution of the storage market just over the last 10 years, you'll see that, for example, we have, as of now, identified 3.9 gigawatt hours of installed capacity. And in the first few years, since 2016, you can see that it was relatively stable around, let's say, an average of 100 megawatt hours per year. Again, as always, a disclaimer with these numbers. These numbers are only the projects that we at AFSIA have been able to identify. There's probably more, but those are at least uniquely identified projects. And look at these numbers as a trend, not as absolute truth, but really as a trend. And then so you see 100 megawatts on average for all these years until 2024, where suddenly we had the big load shedding situation in South Africa and a wonderful boom of installations approaching almost 2 gigawatt hours. That was an exceptional situation, and the next year was a little bit lower, but still a phenomenal increase compared to the previous years. The situation has stabilized a little bit in South Africa, yet installations have grown significantly. And in 2026, so far, we're only like at the end of May, we have identified a little bit more than 350 megawatt hours installed, but we also have knowledge of close to 5 gigawatt hours of projects currently under construction. So you see there's not even enough space on this slide to actually properly show all of this. And as the title identifies, overall, we have identified a pipeline of more than 40 gigawatt hours of projects under development, which is a significant increase. This is not only happening in South Africa. So yes, the big boom originally happened in South Africa, but nowadays you can see that this pipeline is distributed across many countries all over the continent. I present here only just a few, but really storage is taking over the entire continent by storm, different levels, but it's really happening all over the place, and this is very exciting. The main reason why this is happening all over the place is because of the price evolution. These are numbers computed by Bloomberg New Energy Finance, where you see the price evolution from the different elements, the pack, the cells, and the total battery cost, which has experienced a significant price decrease, average minus 11% per year, every year, since 2017. And this is what has really driven the markets in our case on the African continent, because it has opened up a lot of possibilities which were previously not possible. So here on this slide, you can see, maybe you've seen this slide previously. This is a slide where we have presented all the prices, the official prices of grid electricity in every single African country, specifically for CNI customers. You know, there's different price ranges for different customer types. And here we presented the CNI prices specifically, and you see that there is quite dramatic differences between countries. But what matters is that the grids, as we know, in Africa is not always very stable. And so very often customers, electricity consumers have to turn to diesel generators. On average, good year, bad year, nowadays maybe a bit more expensive, but a kilowatt hour from diesel estimated at around 37, 38 cents per kilowatt hour, all costs included. And pre-2024, the alternative to run with a PV system combined with storage solution to make dispatchable solar energy available was a little bit higher than this price. And this is why most people either accepted not to have stable energy or would use a diesel generator when the grid was off. But with the latest price decreases, what has happened is that this average cost PV plus BESS significantly reduced. And again, another disclaimer here, this is just a range of costs that we have seen. Every single project is different. Every project is unique. Configuration of the PV capacity and the storage capacity varies from project to project. The load curve of each client varies. So please take these numbers here as an indication, not as the absolute truth once again. But what is important here is that PV plus BESS has become a viable and very competitive solution for dispatchable solar energy, definitely more competitive than diesel, and in some cases even more competitive than the grid itself. This is why we see so many cases of people turning more and more to solar storage all across the continent. This is just a quick introduction, and all this will be discussed in depth throughout the next 4 days. And I want to give you a quick overview of all the exciting conversations that you may expect in the next few days. Today, we're going to be talking about technology specifically. You see here a quick overview of all the amazing speakers who have accepted the invitation. Thank you very much to all of you, and who will share their expertise about each of these very important aspects of storage from a technological point of view. Tomorrow, we will talk about projects. And again, we have some of the best developers and financiers in the space, active all over the continent, doing amazing projects, and they will tell us a little bit more about key elements to make these projects happen, what works, what doesn't work, and how to prepare your next project. Thursday, we will do some more specific deep dives, especially deep diving into storage related to mines, to industry, and to data centers. And then we will also have a panel discussion built as a dialogue between different key stakeholders to make a project happen, understand what is important for each stakeholder, understanding how a project plays, what are blocking elements, what are enablers, and hopefully serve as an inspiration for future projects of yours. And then finally, on Friday, we will have a broader and summarizing discussion about the Africa storage market outlook, with two panel discussions focusing on the overall market, and then another one also focusing specifically on regulation and policy, which is a key element right now in this nascent storage industry in Africa. Very, very exciting week. And I thank once again all the speakers who have accepted the invitation and who will be sharing their insights with us later this week. And as a last word, I would also like to thank our partners who make this event possible this week and also throughout the year. Thank you so much for the four of you to believe in this conference, to support us in the organization, and to make it possible to welcome so many listeners once again this year for the 6th edition of the e-conference on storage solution. So with this, I hand over back to Salim, who will introduce you our first speaker of the week.
Thank you very much, John, for delivering this keynote speech and for respecting the timing. I'm very excited to this discussion, but just as we usually do, our traditional house keeping rules, I wanted to remind the audience that you should use the Q&A box for all questions and use the chat section for connecting. So please, we will be taking questions, but we advise you to use the Q&A. This is one thing that I wanted to ensure that everybody understand. And now I will introduce our first speaker of the day, Cameron Van Eden, Technical Manager at J. Cameron, you can turn on your microphone and your video. All right.
Thanks for the welcome and thank you to everyone.
Yes. So Cameron will be discussing about the hybrid energy system for CNI. And Cameron, I hand over the speech to you to deliver this amazing presentation. Thank you, Cameron.
Okay, perfect. Thank you. Let me just quickly share my screen. Okay. Good morning, everyone. Thank you for the opportunity to speak here. It's quite a pleasure. As mentioned, I'm Cameron van Yerten. I'm the technical manager at JS Hodler, specifically for the SADC region. Today, I'll be discussing hybrid energy systems, specifically for industrial operation across Africa. Across the continent, industrial operators are facing increasing pressures from grid instability, rising electricity costs, diesel dependency, and growing operational energy risk. At the same time, battery energy storage systems and hybrid microgrid systems are becoming more commercially viable, more intelligent, and more scalable. What we are now seeing is a significant shift from energy storage being viewed simply as backup power toward a core operational infrastructure asset for industrial operation. When we look across many African industry environments today, the energy landscape has fundamentally changed. Historically, industrial facilities have mainly focused on securing access to electricity. Today, the challenge is much broader. For industrial operators, they now require energy systems that are reliable, predictable, financially stable, and have operational resiliency. Many facilities are operating in an environment where grid reliability is deteriorating, electrical energy tariffs continue to escalate, and diesel fuel costs also remain to escalate and are quite volatile at this current stage. For operations such as mining, manufacturing, agriculture, telecommunications infrastructure, and water utilities, energy instability directly impacts productivity and operational continuity. Even short durations of outage can create production loss, operational downtime, equipment disruption, and increased operational cost. At the same time, many organizations are under increasing pressure to improve sustainability, performance, and reduce carbon emissions. As a result, industrial operators are increasingly turning toward hybrid energy systems that combine solar PV, battery energy storage, generators, and intelligent energy management. So specifically, what is a hybrid energy system? At its core, a hybrid energy system integrates multiple energy sources into one intelligent operating platform. Typically, these systems combine solar PV generation, battery energy storage systems, utility grid supply, and generators, as well as EMS or energy management system. The EMS acts as the intelligence layer for the system, which constantly monitors the energy demand, the solar generation, the battery state of charge, grid conditions, and generator availability. Based on the information, the system is able to dynamically optimize the energy flow in real time. This enables several key operational functions, including peak shaving, load shifting, backup power, renewable energy integration, generator optimization, and seamless on and off grid operation. What makes a hybrid system particularly valuable is that they allow industrial facilities to move away from relying on a single energy source. Instead, the operator can gain flexibility and reliance on an energy platform that is capable of adapting to changing conditions. One of the major advantages of hybrid energy storage systems is the flexibility across multiple industries. Different industries typically face different challenges with regards to the energy needs. For mining operations, the focus is often on weak grid support, diesel reduction, and operational stability. For manufacturing facilities, peak demand management, tariff optimization, and production continuity become major priorities. For agricultural sectors, hybrid systems can support irrigation systems, cold storage, and remote farming operation. With regards to the telecom infrastructure, battery storage helps reduce generator runtime and fuel logistics costs at remote tower locations. For commercial and industrial facilities, more broadly, hybrid energy storage systems help improve energy cost, reliance, and renewable energy utilization. What we are seeing increasingly is that energy resilience is becoming a strategic operational requirement rather than a simple utility issue. Another key factor to understand with regard to modern energy storage systems is that they deliver value across multiple operational layers simultaneously. Traditionally, battery systems are often viewed mainly for backup power. Today, industrial energy storage systems create a much broader value stack. At the fundamental level, the system provides backup power, energy resilience, and operational continuity. Beyond that, operators can use energy storage systems for peak demand reduction, solar optimization, diesel reduction, and energy arbitrage. This allows facilities to reduce their operating cost, optimize tariff structures, improve renewable self-consumption, and reduce generator dependence. In many industrial applications, the value of operational continuity can exceed the direct energy savings. Avoiding production downtime often creates great financial benefit. What this means for energy storage systems transforms energy into a fixed operational cost, into a controllable and optimizable strategic asset. Before discussing JA solutions further, I'd like to briefly introduce JA Solar and JA Energy Storage. JA Solar is one of the world's leading renewable energy technology companies with more than 117 gigawatt of cumulative global shipment and operations across 180 countries and regions. The company is recognized globally as a tier 1 bankable brand and is consistently ranked within the world's leading solar manufacturers. For industrial customers, bankability and long-term support capabilities are extremely important considerations when deploying energy infrastructure. Our focus at JA Storage is to deliver intelligent energy storage solutions specifically designed for utility, commercial, industrial, and hybrid microgrid applications. One of the key strengths of an energy storage business is the ecosystem of strategic technology partnerships supporting the platform. Battery energy storage systems are highly integrated technologies that combine battery cells, PCS systems, EMS platforms, thermal management, and software intelligence. To deliver reliable systems at scale, collaboration across the supply chain is essential. Our partnerships support advanced battery technology, PCS integration, microgrid capability, intelligent manufacturing, and global deployment capability. This enables us to deliver integrated solutions rather than isolated hardware components. Moving on to our first product, the JA Planet Commercial Industrial Platform. The system is specifically designed for commercial and industrial applications where operational reliance, energy optimization, and reliability are critical. The platform combines liquid-cooled lithium phosphate battery technology, intelligent thermal management, advanced safety architecture, and AI-driven operation for monitoring purposes. Safety is obviously a critical consideration of energy storage deployment. The system includes a 3-tier fire protection system, real-time thermal runaway detection, and integrated monitoring system. From an operational perspective, the system supports peak shaving, energy arbitrage, and renewable integration. One particularly important area is predictive maintenance. Using AI-driven monitoring and remote diagnostics, the operator can significantly reduce downtime and improve long-term operational reliability. The modular architecture also enables scalability for larger commercial and industrial deployments. One of the most important and relevant areas within the African market is hybrid microgrid systems. Many industrial facilities across Africa operate, as mentioned, with weak grid conditions, unstable grid, and remote environments. In these applications, hybrid energy storage systems become critical for operation rather than simply for energy-saving solutions. Our microgrid energy storage system supports PV integration, battery storage, generator integration, as well as intelligent EMS control. One of the key capabilities is a seamless on and off grid switching under 20 milliseconds. This allows the facility to maintain stable operation during grid disturbances as well as outages. For remote industrial sites and mining operations, hybrid systems can significantly reduce diesel consumption, generator runtime, fuel logistics cost, and operational risk. At the same time, operators gain improved energy resilience, better power quality, and greater operational predictability. The systems are also highly scalable, supporting deployment from smaller commercial applications to multi-megawatt industrial microgrids. Now, if we look at a simplified overview of a typical hybrid operating architecture. At the center of the system is the EMS, which controls the energy flow between the PV system, battery energy storage, utility grid, generators, and facility load. During the daytime solar production, PV generation supplies the facility demand while excess energy is stored within the battery system. During peak tariff periods, the energy storage system discharged to reduce grid demand and minimize peak charges. During outages and unstable grid conditions, the system can transition seamlessly into backup or islanded operation and provide the load with the necessary requirements. Generator system can also be optimized more efficiently, reducing unnecessary runtime and fuel consumption. Ultimately, the goal of hybrid control is not only for energy savings. It is operational optimization, ensuring energy reliability, stability, resilience, and long-term cost efficiency. This slide simply highlights Jay's deployment of energy storage hybrid projects across different applications and scenarios. The projects shown here include commercial and industrial energy storage deployments, PV integrated systems, hybrid microgrid applications, and utility scale projects. What is important is also to note the operating environments and the diversity thereof, as well as the relevant use cases. These systems are deployed across industrial parks, commercial facilities, remote operating environments, and integrated renewable energy applications. What we're also seeing is an increasing deployment of hybrid energy systems that combine solar PV, BESS, EMS platforms that greater support flexibility and energy resilience. Across the African market, it is particularly well suited, for energy storage deployment due to growing energy demand, grid instability as mentioned, remote operating environments, as well in the increase in renewable energy adoption. As the technology continues to mature, the system economics improve, hybrid energy storage is increasing and becoming part of mainstream industrial energy infrastructure rather than a niche technology solution. To conclude, hybrid energy storage is rapidly becoming fundamental technology for many modern energy storage systems. Industrial operators are no longer looking for energy supply; they are looking for operational resilience, energy predictability, flexibility, and long-term stability. Hybrid systems combining solar PV, battery energy storage, EMS platforms, and microgrid capability are enabling exactly that. Across Africa, we believe that hybrid EMS systems will play a major role in supporting industrial growth, energy resilience, and a broader energy transition. Thank you for your time, and I look forward to the discussion and the questions. Thank you.
Thank you very much, Cameron, for this amazing presentation. Now it's time to take some questions. This is the time to drop your question in the Q&A box. We only have 10 minutes to take everything. I'm picking up the first question from Sami. Sami from Kenya is asking, what are the main technical and financial considerations industries should evaluate before integrating solar, storage, and backup generation into a hybrid energy system?
With regards to, I'll start with the technical solution. It's what is the client's requirements in terms of availability of electricity cost, and there is the availability and also the effect on their operational demands. If the client is significantly affected by any sort of downtime or defects of operation that results in a loss of any sort of income, that will also then obviously play into in a way your payback period, as you are essentially not losing any income that you would have had lost during that time. With regards to the financial, your especially with the increase in your diesel cost as of recent, and as well as the escalating electricity cost across Africa, it simply is towards the benefit of and the financial model of a hybrid energy system, and also then reducing the cost of the client's electricity consumption, and also bringing that towards a fixed set value as the electricity and diesel costs increase from the utilities.
All right. And another question from Michael. Michael asking if you can share example of industrial sector in Africa where hybrid systems are already delivering strong performance and measurable business impacts.
So typically the scenarios you see within the hybrid systems is typically within your manufacturing sector, where if the client experiences any downtime, it's directly related to their operational output and the production, and therefore also they typically would incur a loss due to the lost product that could not be manufactured. That is typically let's say there's multiple systems across the African region where that is the current situation. And also by implementing hybrid energy system, the client is more ensured of the energy availability. It's more predictable, and therefore they do also not incur loss due to any downtime.
All right. And if you can also allow me, I just leveraging on the fact that I'm discussing with you to ask one personal question. I've seen different OEM mainly interesting in the mining markets, in the mining sector.
Yes.
And I was just wondering why now? Why are they now all interested in that industry specifically? Because I happen to interact with different OEM, and recently I've really received those requests of, yes, we would like you to connect us with mining sector. We now have a particular solution for them. So why is it happening now and not before, since we already know that there are part of large energy consumer?
Yes. So what I've seen is also due to the adoption of let's say renewable energy as a whole, the case studies that are available, it's also more out in the market, as well as the increase in the technology and the scalability of the technology. Your mines are quite large consumers across most African countries. Most of the OEMs, including ourselves, offer now up to utility scale solutions up into the multi-megawatt range, able to support mining operations, the specific generator integrations, backup power, all of that. So it's a combination of the adoption as well as the advancement in technology, as well as the cost reduction, as we saw earlier in terms of the battery, as the technology increases.
Okay. Last question before we hand your presentation, Cameron. A very interesting question
Right.
from Abdullahi Yahaya, asking how are your PCS designed to manage tender in Africa, in African weather and weak grid integration?
Say again, how are PCS designed?
How your PCS design is designed to manage tender in African weather and weak grid integration.
Okay, so from the PCS point of view, or from a solution point of view, with regards to the weather constraints, our solutions are specific to the environment, corrosion, the temperature within the African environment as well. Especially for if you were to have a remote application or severe or extreme weather ranges, that is specifically designed for that, and for weak grid conditions. The PCS will obviously monitor the grid continuously, and once the grid goes out of bounds or is essentially lost, the PCS will disconnect from the grid, so to ensure that the waveform and the parameters that go through to the load do not damage the load as a whole. That is, it's specific to each country and specific to each customer, depending on how critical their loads are and also how sensitive the equipment would essentially be.
All right. Yes, thank you very much, Cameron. Even though there are some questions that I couldn't pick, but we are already heading to our next session of the day. Yes, Cameron. Thank you. You can turn
Okay.
off and on your microphone.
Okay, perfect.
Cameron.
Thank you very much.
Thank you.
Cheers.
You're
Bye.
welcome, Cameron. Now, I'm happy and pleased to introduce the next speaker of the day. Titus Koshen, you can turn on your microphone and your camera.
Hello, hi.
Perfect. Perfect. You already started your presentation.
Yeah.
Yes. Titus is our next speaker of the day. Titus is the Energy Storage System Head of Technical at GINCO, MEA, and CA region. Titus will be speaking about the storage technology for CNI. Titus, welcome for this session, and to you,
Yeah, thank you, Salem. And one is just to say thank you also to the previous speakers, John and Cameron, for the exciting introduction, and also exactly laid ground to my presentation and also the future presentation as well that we're going to have today. And I think you've already given an introduction about myself, so I don't need to repeat that right now. So allow me to just spend maybe 1 or 2 minutes to also introduce my company. GINCO ESS, or rather GINCO Energy Storage Technology Company Limited, which was basically officially established in 2022. So GINCO ESS is a strategic arm of GINCO Solar, basically focusing into research development and also manufacturing and integration of battery energy storage systems. And also to note is that we also are tier 1 battery energy storage manufacturer as listed by Bloomberg New Energy Finance. And currently, we have a cell manufacturing capacity, because we do manufacturing of around battery cells of 5 gigawatt hours, and also an integration capacity of 37 gigawatt hours. And also notably to note is that we also do a full self R&D, that is from the BMS, the PCS, OPS, and also the EMS as well. And we also do the integration, that is integration of our self-developed components, and also our self-developed plus third-party components as well. And our factory is in Aining, China. That is only close to 1.5 hours from Shanghai. That is fully automated with more than 50 manufacturing processes, and also various, that is more than 200 quality inspection points for purposes of adhering to IS level of quality. And as a manufacturer and also as an integrator, we do basically focus into solutions for commercial and industrial. That is basically the Sangiga all-in-one solutions. And we also have solutions for utility applications as well. That is basically the Santera. So for the C&I, we have the 261 kilowatt hour. That is a 2-hour solution, and also the 522 kilowatt hour, which is basically cabinet solutions. Which are modular in nature. I will show you later on. And also we also have the utility products, which is the Santera Generation 2 and also Generation 3, which comes in 2 different capacities in the same container. That is 20-foot container. That is a 5 megawatt hour for Generation 2 and 6.25 for Generation 3. And mainly looking into just to the final slides to explain more about our C&I solutions is that, like I said, we basically focus into cabinet solutions for our commercial and industrial solutions, and containerized solutions for our utility scale solutions. So for the containerized solutions is that we have 2 options. That is the 2-hour option, that is the 261 kilowatt hours, and also the 522 kilowatt hours as well. That is the 4-hour solutions. And of course, it comes in with special features like you can see on your screen, including, up to 100% DOT, and also the ability to parallel up to 12 units in off-grid applications. And for on-grid applications, we can actually parallel a limited number of units. And we also have the option of having a seamless switching, solution, basically by having an external STS and being able to achieve up to less than 20 milliseconds of the switching time. So with regards to the overall parameters of these particular solutions, that is the 522 and also the 261, is that we are having an AC round trip efficiency of more than 90%, more than 8,000 cycles, basically at 70% end of life. And also, we also incorporated a very robust fire suppression system as well, that is basically aerosol based, that is integrated in the cabinet. So ideally, like I mentioned, this is just an overview of the solutions. You can get in touch maybe with myself, also our team, if you need to know more about our SunGiga and also the Santera solutions as well. So I just want to briefly, look into the C&I based technology. I know Cameron from J Solar's given some insights about microgrid solutions, the technology, the need, the challenges as well. But I also want to build up on that to basically show that the C&I based technology has greatly, advanced for the past few years that is in the industry at large, not only focusing into Africa. There's actually, more focus into battery energy storage systems, which is mainly focusing into storing electrical energy by, using chemical energy through electrochemical processes. And, we have a number of cell or other chemistries that we mainly focus on, including lead, we've had lithium, we've had sodium, which is basically more of the next generation technology, other chemistries like nickel as well, and many others. So I won't really mention all of them. And you see is that all these chemistries, they all have their own pros, and also they have their own cons as well. And also, selecting the right cell chemistry or also the technology depends on a number of factors. And these factors could actually be, could be looking at flexibility of the solution, could be also looking into the safety, could also be looking into factors like energy density as well, and also power density. We could also be looking at, considerability as well, which is a major, parameter that we mainly focus on. I think mainly in Africa is also the element of cost. Glad that, John in the initial presentation did highlight about the cost trends for the last from 2017 until 2025. You could also looking into the cycle life of the solution, which basically determines on how basically the calendar life of the whole solution, the design life as well. Also looking into other parameters like the temperature range. We understand that some parts of Africa, they actually experience extreme temperature conditions up to maybe 50, 52 degrees Celsius as well. So ideally, these are basically some of the parameters. And based on my own analysis, and also which also looks into, we've also seen a couple of reports as well, basically indicating that lithium iron phosphate as a cell chemistry is actually becoming to be a more preferred cell chemistry for battery energy storage systems, because it's actually balancing most of the parameters of the lifespan, the cost, the safety, and also the operational reliability as well. And looking into the different application scenarios, basically mainly common for commercial and industrial, we could be looking at, application scenarios like peak shaving and also load shifting as well. Ideally, focusing into shaving the power demand curve, that is the PDC, and of course, reducing the overall consumption for the case of peak shaving, and also for load shifting as well, which is basically more of focusing into shifting the energy demand times, ideally changing the energy, that is having changes in the energy, and of course using batteries to charge during the peak period, and also very off-peak period, and discharging during the peak period as well. Ideally, to achieve the purpose is basically to achieve a more levelized or balanced daily demand curve. But of course, in this particular case, because as opposed to peak shaving or load shifting, would actually be able to have more of the same level of consumption as well. And of course, also battery energy storage systems also playing a critical role, of course, to improve or rather also advance the adoption of course renewable energy like solar PV, wind ETC as well. Ideally, we understand that most of the renewable energy technologies like solar, it basically does not follow the demand, because sometimes you find that the demand is actually peak during maybe early morning or late in the evening when there is no solar generation. Ideally, we can also be able to use battery energy storage system to store the excess generation during the day, and also be used during the peak consumption period as well. And of course, the other point as well is, battery energy storage systems being used also to play a role to reduce our, dependence on diesel generators. And of course, I want to highlight that, especially for mining areas, mining applications as well, looking at currently what is happening globally, we are seeing a change or rather an increase in diesel prices globally, and of course increasing the costs of production. So ideally, of course, with battery energy storage system, we can actually be able to reduce on on our dependence on diesel generators as well. So ideally, the graphs that we're seeing on the right is basically to highlight to you on the difference between the peak shaving application scenario and also the load shifting as well, like highlighted at the first application scenario for battery energy storage systems. And also, I also want to just look into the different technologies that we're seeing, especially in 2026 and beyond. Of course, this is mainly constrained to what we can see from an OEM point of view, as one of the technology leaders in battery energy storage systems. So there are a couple of trends that we're seeing, and one is basically, of course, the adoption of all-in-one solutions, and not only all-in-one solutions, but also all-in-one, but smaller cabinet designs as opposed to, larger containerized solutions. Of course, the reason for adoption of this all-in-one integration, of course, in single cabinets is basically to reduce, the overall system complexity, to reduce the level of wiring as well, and also to improve the overall operation, or rather the performance of the system. And what do you mean by all-in-one is that ideally looking into having the full, components, that is of the battery cells, the battery pack, and also the battery rack. And of course, having also the power conversion system in one particular cabinet. And also we're looking into having also the other ancillary equipment, including the liquid cooling units and also the fire separation system as well, integrated in one particular cabinet. And of course, most of the all-in-one solutions that we're seeing currently, from top tier one manufacturers is basically incorporating a one rack design, that is having only one rack of batteries or having a maximum of 2 racks of batteries. Ideally, the whole idea is to have it as small as possible and also as modular as possible as well. So like we can see in this particular case, you can have only one rack, or also you can have also 2 racks as well, for purposes of achieving modularity that we are going to look into the next particular, the next few slides. The other trend that we're also seeing is, having a fully pre-installed and pre-commissioned system. So ideally, the whole idea is to lessen, to make sure that the integration role is actually taken care of by either the integrator or also the manufacturer as well. So the whole idea is also to reduce the time used for installation on site, basically to reduce the installation time and also the installation cost as well. So you can see most of the components that we're seeing nowadays basically having this pre-installed and pre-commissioned. And of course, to also have uniformity and uniformity in terms of, in terms of the wiring, in terms of the configuration as well, ideally to lessen the need for on-site installation as well. So ideally, that's what we are seeing from an OEM point of view. And also still looking into the all-in-one solution, that is having in smaller cabinet solutions as opposed to container solutions, allowing us to, we can build small, we can easily scale up the solutions and also maintain flexibility. Look, for the case of, let's say, mini grids, you can actually start with small systems, let's say 200 kilowatt hours, build up to 400 kilowatt hours, all the way to megawatt hour scale as well. And of course, it you need to this aspect of flexibility. It is only not being it from a technical angle, also from a commercial angle as well. We can actually build up on, a flexible layout. We can actually build up on flexible solutions. So ideally, the upfront cost does not need to be, need to be, the developer or the EPC or the owner does not actually need to overstretch on the capital cost, because you can build up the solution as you go. The other point from a technology point of view is also looking into the element of thermal management. Thermal management is basically having in mind that one of the issues that we have, especially with lithium-ion phosphate battery energy storage systems, is actually the susceptibility to thermal runaway. So ideally, one of the ways to mitigate this aspect of thermal runaway is actually to have a very robust thermal management system. So this is not only to mitigate thermal runaway, but also to also assist into improving the overall design life of the whole battery energy storage system. And you find that, we've had air cooling as one of the primary thermal management systems for the longest period of time. But since I think 3-4 years ago, we've seen the introduction of liquid cooled systems, which is basically more of industry standard now for, for battery energy storage systems. And the good thing is that, there's also some bit of improvements in these liquid cooled systems by also incorporating AI algorithms as well. So by incorporating these AI algorithms, you can actually be able to achieve intelligent control strategy for purposes of zonic specific cooling and also dynamic regulation of the cooling agent as well. So ideally, in the current trend, we actually seeing that we have, incorporation of liquid cooling plates on, on each of the battery packs for purposes of cooling at the pack level. And you see also is that these cooling plates are, non-uniform channels, basically bionic flow channels, to basically reduce, abnormal high pressure zones, also to minimize the instances of dead spots, that is temperature dead spots, and also balance, achieve a balanced temperature across all the battery cells. And you can see from these particular graphs, based on our own analysis, we can actually see that we can have optimal temperature control. Looking at, let's say, the dark curve where we can see conventional solution, of course, using air-cooled solutions, where we can have more of an erratic curve of temperature inside the battery pack that is comparing different battery cells, and also as opposed to the current solution, which is basically air-powered, where you can have uniform, more of, it's almost constant temperatures across the different battery cells in the battery pack. The other point is also, like I said, for this thermal management, of course, incorporating liquid cooling is basically to maintain high degree of cooling, and also increase the overall system design life. Ideally, that's the reason why we can achieve up to more than 10,000, more than 12,000, and ideally have solutions, especially for C&I, of up to more than 15 years, basically because of the technology that I was actually discussing in this particular slide, which is basically air powered, and also having some very complex algorithms. And the other point is the level of safety. Like I said, there is also need for battery energy storage systems. In as much as we're saying the battery costs have really gone down, it's also still a bit pricey. It's also still a bit expensive as well, looking at the whole ecosystem, especially for microgrids or C&I applications. So there is also need for enhanced safety, and also multi-level safety that is in different dimensions. So looking into safety from a structural point of view, safety from an electrical point of view, and also from looking into the other element of also fire safety as well. Ideally, to ensure that we are working on safe environments. And, I usually say that, we need to protect the structure, we need to control the current, and also prevent the fire for a reliable energy storage solution. So you find that, ideally having also different dimensions of safety from cell level, from pack level as well, where we have insulation, non-conductive insulation media as well, explosion-proof design of the battery pack as well, and also fire-level fire suppression system, which could also be incorporated in the battery pack. Then also looking at safety also from the rack level, where we have, most of battery energy storage systems incorporating temperature, smoke sensors, or basically the different elements of the fire suppression system. And also looking at also from a system level, basically from the whole cabinet, where we can have the full fire suppression system, and also having a cabinet, because it's a closed compartment, we expect also the accumulation of explosive gases, basically looking at CO or maybe hydrogen, because of the chemical reactions that usually happen in the battery cells, especially focusing into lithium. So ideally having an explosion-proof design by incorporating either ventilation or deflagration vents that is basically in compliance to NFPA standards. That is NFPA 65, 68, 69, and also 855 as well. The other elements that also want to talk about is, like I mentioned in the previous slide, is that safety can be in different dimensions, and more focusing into safety, fire safety in this particular case, is that you find that it should be say that it actually should be not negotiable that having a fire suppression system in the cabinet, or rather in a battery energy storage system cabinet. So these fire suppression systems that we've seen in the industry is basically more of intelligent, sometimes also incorporating AI as well. for purposes of basically ensuring rapid detection of abnormal temperatures or also smoke as well, and also achieving also automatic suppression of fires if if it happens, and also to be able to have also an efficient ventilation or deregulation to basically release the accumulation of gases beyond the accepted limit in the battery cabinets. So all this basically done to be able to to make sure that we can have the system to be more of a fireproof system. And you can see that looking at the different dimensions, looking at having early warning, basically by incorporating this in the battery management system to be able to monitor the temperature. Also, you may also having a number of sensors as well, either in instances of smoke level as well, because so that we can either have this warning levels by having this in audio alarms. We can also have these warnings to be able to stop the the battery, or rather the PCS, from charging or discharging, and also to be able to activate also the explosion venting mechanism, or to be able to also to have the temperature smoke sensors to be able to send a signal to the fire suppression system to automatically.
Sorry, Tatas, just for timing consideration, we wanted to take some questions since the next speaker is getting ready, if possible.
I think I'll finish in the next 2 minutes.
Okay. Yeah. Perfect.
So ideally, with this fire suppression system, can actually be able to either do early warning, explosion venting, and also fire protection system as well. Most of the fire suppression systems, fire protection systems, could actually be gas-based, but we've also seen a trend where we can also incorporate water fire protection as well, where you can flood the whole cabinet with water as well. So this is basically an add-on, or rather an optional strategy as well for fire suppression system. And the other thing as well for the C&I solutions is the adoption of grid forming PCS, or other grid forming inverters as well. Ideally, having these grid forming inverters which are able to form the grid, actually able to act as independent voltage and also voltage sources, be able to build up the grid voltage and also the frequency, be able to also do inertial support, and in most of the instances also be able to have black start capabilities. This is highly essential, especially in most of the regions where we have very weak utility grids as well. So ideally, we can have this black starting capability. And the other thing is also the incorporation of AI, actually full stack AI. One, having AI also in the battery management system for purposes of smart monitoring and also warning as well. Also having incorporation of AI as well in the OPS platform, so that we can be able to see the health of the battery cells and also the life cycle, the life prediction of the battery cells as well, and be able to also assist in self-diagnosis and also remote repair of the systems. Then also having AI incorporation also in the EMS level, so that we can be able to actually be able to have efficient optimization and also maximize the overall round trip efficiency of the system, and also be able to see on the energy optimization, energy forecasting as well, and also price and load forecasting as well. So ideally, this is basically incorporation of artificial intelligence. I've just shown on the right side on how we've done this from the Junko platform. So this presentation will be available for your review later on. So I think that's the end of my short presentation. So I'll welcome questions. And also, if you have any specific questions that we're not able to answer this particular case, you can also reach out to my email address, and I'll be able to, discuss on a personal level.
Thank you very much, Titus. I have a lot of questions since your topic is a very interesting one. as it's subject to evolution. You are talking about the technology, and we know technology are already subject to evolution, and we don't have control over it. So one question from the audience, one question from let me read the name, from Sam. Sam is asking, since technology is subject to evolution, which innovation do you see, do you believe will have the biggest impact on performance, safety, and affordability in the next few years?
Yeah, I would say, looking into that aspect of performance, I would say that the evolution of the thermal management systems, that is not only liquid cooling, but also incorporation of artificial intelligence as well to have precise temperature control. Because you see, look, especially looking into thermal management systems, that is lithium and phosphate battery energy storage, or other battery house, you see that temperature is basically an enemy. And of course, having a system could actually be able to enhance the overall system operation. And also, look, the other thing is that, like I mentioned to you, most of the battery energy storage systems actually having a typical actual round trip efficiency on the AC side, factoring in auxiliary consumption of around 90%, or let me say realistic from the CNI level. So ideally, that means that we're losing close to around maybe to around 9 to 10%. That is to auxiliary consumption. And basically this 8 to 9%, the major contribution, close to 80 or 90%, is actually auxiliary consumption because of the liquid cooling system. So if we can have a cooling system that is highly efficient and also uses less power as well, then that could actually be able to assist us to, to also improve the overall system efficiency to maybe values of, let's say 95, 96 or 97%. That is basically, just being very optimistic.
All right, I'm just taking one question, and I would like you to just be quick in responding to it. A question from Sagni is asking, which class of battery are currently Jinko using?
Currently, I assume that you're talking about the capacity. Is it we following the basically the industry trend? So we have two options: 314 ampere hours, that is 3.2 volts, 314 ampere hours, and also 3.2 volts and 587 ampere hours. That is all lithium iron phosphate.
Thank you very much, even though there are a lot of questions. I'm going to head to the next speaker. Thank you very much, Tatas. You can now turn off your microphone and camera.
Okay, thank you, Salim. Bye-bye.
You are welcome. Welcome on board, Sami. Wait, you can also in your turn switch off, turn on your camera and mic. Sami, I hope you are with us. Here you go, we go.
Hello.
So Sami, welcome. I'm going to introduce to the audience. Sami Wait is the head of design and engineering at Chloride Excite. And here we will discuss about advances in CNI and large-scale storage technology. As you have seen, we have started to talk about CNI, and now it's also time to talk about large-scale technology. Thank you very much, Sami.
Thank you, Salim. I hope I'm audible.
On my side, I don't have anything to complain.
Awesome. And my screen is also visible, I think.
It's very perfect.
Fantastic. Thank you very much. Good afternoon, people from the East, and good morning still from guys in Central Africa. Today, I'll just talk very briefly about advances in energy storage. Actually, I will try and save some time because most of the aspects we are going to talk about or skim through have been already been talked about. Brief history about Chloride. We are a very young company. We are only 63 years old, but with a bit of experience especially in energy storage. Huge footprint in East Africa, both from automotive perspective, energy storage perspective, water heating, and PV perspective. All right. what are we looking at in terms of the new things, the new wannabes in energy storage? All right. Now, the industry has moved from the normal energy storage, which used to be an on-demand energy storage. Now we are into the long duration energy storage perspective. Okay. So in principle, in the previous past, people are looking at two hours peak storage capacities, but now we've moved from the 2 hour space to 8+ hours in terms of capacities. When the other most important aspect that is becoming very key is the safety, the chemistry to which the batteries or the energy storage applications are coming in. Their safety and chemistry is also becoming very important. We've seen a number of vanadium flow solid state batteries coming up now already in the market. And as previously mentioned, with the past speakers, AI has become very key in managing all these aspects, because now you're integrating a lot of energy sources. It's no longer about one or two energy sources, so we need to prioritize, all right? So in terms of technology, just to compare, we compare the various technologies. In the most recent lithium-ion application, most of them, they're used for peak shaving, as it has been mentioned before, and also in EV hubs where you have mobility. They're also used a lot in EV application. In utility also, they're used in energy management, and also supporting supporting anything to do with the excess energy or energy on demand as it's required. All right, and we've seen currently the advancement. What is happening in the market is AI is becoming a very key role when it comes to this particular application, because now AI is what is using. We're using AI algorithms to ensure that you optimize on your most important or the cheapest cost of energy that you need. Then we also have the ultra high capacity lithium options, where most of them are used for long duration of energy storage. And the advancement in these technologies currently, most of them are talking of over 25 years service life. Okay. And then ultra use thick electrodes. They're using very thick electrodes. On flow batteries, now they're coming in non-flammable options that can give you 5 hours plus of discharge and up to 200 megawatts of energy and 1 gigawatt of storage. When it comes to hybrid options, where you can do, you can combine two topologies, maybe supercapacitors and lithium ion. This used to be a millisecond sort of energy storage, but it's now becoming longer, because now you're putting in several technologies together, and then you're able to get longer duration. Then we also have the new solid state batteries. And these are becoming big in terms of looking at your energy density, because now you can get up to 500 watt hours per kilogram, which is quite decent based on what is available. Okay. When it comes to CNI, most important is we are now looking into intelligence and reliability. Okay, so basically what you're looking at, people are now testing in terms of how robust are these units. Are they able to withstand typical weather, especially in the tropical regions? Okay, harsh operating condition. Nowadays we have you no longer need a powerhouse. You're getting an energy storage that comes as an all-in-one pack. Okay. The other very important aspect is we also are having AI-driven strategies. Basically, it's looking at what source of energy do you use at what particular time. Okay. Then the most important aspect again when it comes to installation is you're looking at a very simplified deployment aspect. Okay, it's a plug and play basically. So where we used to take several days or weeks to install a system, now you're doing it in a matter of hours or minutes and your system is up and ready. Okay. The most important in terms of core enablers is basically large format cells, as it's been previously mentioned. Now we can see cells going up to our 320 Ah. Okay. Now we're looking at getting to 600 in the next few, maybe in the next quarter or so, we'll have people talking about 600 AH, okay? Which now that will ensure that we reduce in terms of costs and you have less racks in a unit. Liquid cooling has also become very important because it improves your thermal efficiency and also uniformity. High voltage, because that also increases efficiency, okay? And AI-driven, we've already talked about. In ESS, we've mentioned about peak load or peak shaving. Basically, you're looking at, instead of you applying for high capacity in your utility to ensure that you're able to take care of your peak loads, you can have an energy storage whereby all these high peak times are being taken care by energy storage, which has become very, very important to most industrial users. When it comes to liquid cooling, again, most important is efficiency in cooling, because now it's no longer about just having an area that hotspots, because when you're looking at air cooling, it used to have you don't have uniformity in cooling, but now with liquid cooling, you're able to achieve uniformity across the cells and depending on the location. Okay. Safety and insurance is another very key aspect when it comes to energy storage, especially for systems that are being financed by third parties. It's very, very important that they comply to safety standard, and insurers are now becoming critical. They might need to ask for several safety standards, the UL 9540 or the 9540A, about system safety and fire suppression, and also how are they spaced, okay? Then the other mandatory aspect about the cabinets is they must have gas detection, especially for hydrogen, so that in an event any hydrogen gas is detected, they have a way of shutting down the system. Ventilation is another very important aspect. Deflagration of venting basically is to ensure that anytime you have pressure inside getting to a certain level, there's a valve that can open to release that pressure. Then lastly, remote emergency power off, which is also very critical when it comes to these systems, okay? In form of transformation, what are we looking at now? Data centers are no longer just data centers, but also becoming critical power buffers, because they have this system and they're able to, because it's no longer one energy storage system. You can integrate several energy storage systems so that in an event there's a need or a surge somewhere that you need energy, the AI can monitor that and quickly shift energy towards that area. If you have weak grid scenarios whereby you do not get your frequency to standard or voltage drops, you're also able to get these CNI units to come in, and they also come in very in all-in-one. We've talked about being enclosed in one pre-configured thing. You have your PCS, your battery, all assembled in one unit. You don't have them segregated. Okay. What are the summary takeaways that we can take about that? Is the first thing is CNI energy storage is just no longer about power backup. It's basically becoming an intelligent way of generating revenue, and also you're getting them connected to a bigger network so that they're able to send power from one area to a needy area. Okay. For large scale application, you're looking at storage systems are no longer about 2 hours or a couple of seconds or minutes. They're now moving to 8 hours plus. So they need to be having very dependent grids. Okay, hybrid systems. We've talked about supercaps being integrated together with lithium ion. Now this offers very good, especially if you have a grid network that has instabilities or with loads that are not very stable. They have peak loads. So if you have a hybrid system that integrates lithium ion together with supercapacitors, you're able now to get all your energy smooth grid that has very stable voltages and frequency. And the last aspect is all about the safety and cooling that we've already discussed about. So I think that summarizes what's happening in the scope, and I'm open now for any questions.
Perfect, Sammy. You just anticipated everything, and I really appreciate the summary that you just presented, because there are some questions that was addressed in the previous session that we did not address. We did not pick them, but since you also slightly mentioned about them, I'm going to start with them, mainly on the safety and cooling. Not to make a comparison, but Jinko was just mentioning that about the AI integration in the liquid cooling system. But there is a question that was asked by the audience if this also can be integrated in the air cooling system.
Sorry, if it can be integrated in the what? Sorry, I
Yeah,
missed that.
in the air cooling, because in the previous session we had where Titus was highlighting about the AI integration in the liquid cooling, and we had a question also. There is an attendee who wanted to ask about the air cooling, like how is it integrated, or if it can also be integrated in the air cooling system.
The challenge with air cooling system is it's very difficult to manage the flow. Liquid cooling is easier. You can you can channel liquid cooling to the areas that you want to take them. Air cooling becomes difficult. So that's why most manufacturers have moved from air cooling to liquid cooling, because there you're able to integrate, to focus the areas that you really want to cool. Air is a bit challenging to work with or to move, especially if you have bigger cabinets. Okay, that's the biggest challenge.
Now I understand why you actually asked the question. So does it mean that so far there is not yet a system that has integrated AI in the air cooling? Is it what you meant, or because you just said that it what?
Affirmative to that, because it's very difficult to control air. Okay. Then have a channel. It can flow in any direction.
All right. So yeah, this is a question that I really wanted to get back in, and a question from Maya Shah. Would end user oversight tools like energy management apps become a key driver in the evolution of energy storage system?
Yes, they are, because this is now what will optimize your energy, because your energy management system is what will know that your load is now exceeding your peak demand. So if you have already an EMS system, that is now what's going to be controlling your different sources of energy. It knows that it's daytime, so you have solar. So priority will be given to solar. If it's at night, maybe it goes back and says priority will be on energy storage until you get to your energy storage gets to a certain level, then it can move into the grid. If grid is not there, then it can call in maybe a third or fourth source, which would be the diesel generator. If the diesel generator is not there, then whatever energy that you still have in your energy storage system becomes your backup. And then at that very time, it flags that as an emergency, because it says you're now on your last option of your source of energy. So EMS is a very key component in systems nowadays.
All right. And one more question from Patrick. Patrick from Zambia is asking, what variations in the speakers, what is the variation the speaker is seeing in the battery pack pricing?
Wow. Prices have been coming down until last year, Q4 last year, when the prices started going up. And there are quite a number of key aspects that have been affecting the pricing. Number one is availability of raw material, which has been a challenge, which has forced the prices to go up. And then the political conflict within certain region has also had a very big impact, because that affects the free moving of products from one region to the other. So that also has affected the price positively. So the prices have basically been going up.
All right. So I'm going to pick one more question because we have time. And even though I believe this question would really fit to be addressed to a developer,
Okay.
but since it has been asked, I'm going to raise it, and I'm pretty sure that you might have the answer to it. And from your experience, what are the operation challenges utilities and developers face when deploying large-scale storage system in Africa? The operational challenges.
Yes. Okay. I know the first aspect is utilities. Normally, they have their quota of energy that their customers have. The only challenge comes in is sometimes you have peaks that are not, they have not been factored in. Or if you have lots of grid integrated solar systems, it means that there are certain times if you do not have sufficient insulation, it means that your grid demand goes up as opposed to your normal time. So that has been a challenge, and that's why energy storage now is becoming a very popular, especially a very popular aspect of solution to ensure that you have a stable grid before you bring in all your other sources of energy. Because with energy storage, you don't have time to wait to fire maybe a turbine, a second or a third turbine in a particular generation station. So a lot of utilities now are moving towards commercial energy storage to ensure that they have that as a dependable source of quick energy demand.
Thank you very much, Sami. And we will close your session by here and now jump to the second one. Thank you. You can turn off and off your camera and microphone. And I'm going to welcome Henry Sanele from Huawei. Henry, you can turn on your mic and your camera. Perfect, Henry. I'm very happy that you are with us. And Henry is the Chief Solution Architect at Huawei Digital Power. Henry will discuss with us about safety, bright future advancing energy storage safety to new heights. I'm going to hand over the presentation to you, Henry.
I'm just trying to see if my video is working.
If your video is working, it's not working. Probably, can you put it in the presentation mode?
Let's see. First, let me just fix my video.
Okay, we can give you 1 more minute to fix your video.
Yeah.
All right, Henry, since your video is not working, can we jump to the presentation directly?
Jump to the presentation if my video is not showing right now. I hope you can see my video.
We can see the presentation, but not the video, because apparently there is no video in your presentation. That's why I requested you to start your presentation directly.
Good morning, everyone in Southern Africa, and good afternoon in East Africa. Okay, so my presentation today will be more on the safety of the energy, how as Huawei we actually ensure and making sure that the safety is actually adhered when we're doing this project, and also when we offer our product. Okay. Okay. So one of the key safety challenges we actually see across the BESS, we've seen that there's a high trinity also on the voltage and current, high current and high voltage, of course, also density. So we're talking about plus 5,000 cells that are connected in series and parallel in a 5 megawatt hour BESS. We also talk about electromechanical inconsistency in terms of your overcharge and deep discharge of the cells that will actually cause your thermal runaway sometimes. We also talk about, sorry, see that my presentation is gone. Okay. We also talk about grid uncertainty, where there's a traditional architecture actually on the vulnerable grid disturbance. When you're actually using the centralized PCS, where you actually lose a lot of your racks when you're having a central as compared to string PCSs. We also talk about a low degree of digital management in terms of your low visibility and monitoring of your condition and status. So let's dive in on the thermal runaway and cause and effect. So you will see that a lot of these effects, they actually come from your runaway, thermal runaway. So we're talking about external high temperatures. So when you're actually having your HVRT from your grid and there is a backfeed current that is happening, you'll actually have issues on your battery. So your battery will have external high temperatures on your current because the current will be high coming from the grid. We also talk about the external short circuit that might happen also on your system. We also talk about voltage and over voltage and over current on over discharging when your battery is actually charged and you're actually over discharging it. Puncture also that happens also, especially when you do the logistics of your solution, of your products, and also external defect that might happen in your battery, and also deformation that might also happen during the logistics and stuff. So we've seen a lot of these effects that are actually happening in a couple of places like China. We've seen it also in South Africa. One of the references I'm going to show you also is the South African bank. We've seen it also in Korea, Australia, Germany, and other places where we're actually having these issues of fire. So this is one of the cases in a major bank in South Africa, Standard Bank. So we actually had a problem on this where the battery caught the fire. This was caused by the thermal runaway that happened on this battery. So what are we saying as well? We're saying that the safety management actually has to be ensured for best safety in terms of your battery pack. So when you supply the battery pack, your battery pack must actually have some of these requirements, such as your preventing of arc. We also have prevention of heat spread and also prevention of fire propagation. So with casing we're using on our battery pack of our cells, there are 104 cells inside. We're actually using a metal battery case, and also insulations that will actually prevent these arcs and from happening and this heat from spreading inside your battery pack. So this case only can actually prevent fire from, can actually withstand fire of 1,500 degrees Celsius. So also on the Smart Health Card, we actually also offer risk warning, proactive protection, and also smart O&M. So that's what we offer. So in terms of the insulation inside that battery pack, you will see that the industry norm actually uses the edge coverage. We actually use the full coverage in terms of the protection of the insulation. So this will actually save you from a lot of problems. So whenever there's a cell, because I said to you, we've got 104 cells that are actually lined up in each and every pack. So if one cell is catching fire or one cell is catching heat, it can actually not move away or from one cell to another cell because of this full coverage we have on our battery cells. Okay. So we also use the ultimate insulation in terms of, we call it a Mica. So this is your thermal shock resistance insulation that can actually expose extreme heat of plus 1,000 degrees Celsius. So this is the Mica layer we actually put for our battery pack to prevent such. And our Mica layer can withstand 1,500 degrees Celsius. Unlike the industry that actually uses PVC. So PVC is actually flammable. So we also use polypropylene layer. This is actually for compression and resistance on insulation of these cells. And we also use the ceramic composite layer in terms of your high temperature insulation, because we believe that ceramic can actually withhold heat without actually, like your metal. A metal can actually move share the heat with another metal, and then we actually have a problem, and then we start a fire. So the ceramic is actually continuing the heat and actually can withstand high temperature insulation on that. So on a pack level itself, we're talking about the pressure relief. So what happens now if there is a pressure? Because the question will be like that. What happens now if there is a pressure now in one of the cells inside or in the pack? So we actually have, we call it a high strength withering steel. This is actually your cover, that is actually 1,400 degrees Celsius. That can actually prevent that heat from happening. And we also have a pressure relief valve in our cells at the back. So this is a directional relief valve. So if ever one cell in each and every cell inside here, 104 cells is experiencing any heat, it will actually remove or will actually release the positive pressure with the air tightness on this. And we also have positive pressure oxygen blocking, directional pressure relief, so on these batteries, so to actually prevent the combustion triangle, so to prevent the oxygen that is actually going to come in. Looking at distributed exhaust design, you can see on the industry, they actually do the container level smoke and gas exhaust management. This is actually what the industry does. So at Huawei, we don't do that. We actually do the proposed solution that is actually on a pack level itself. So the smoke exhaust management actually offers a high operational flexibility in terms of actually releasing the pressure from inside to outside, to actually try and prevent the fire that might cause or that might happen on this pack. And because if this pack is catching fire, probably the other pack will also catch fire. So this pack level smoke exhaust management actually offers the high operational flexibility in terms of in looking at compared to the container level that we actually do. So also on the visualization, we actually do the optimized operation in terms of your each and every pack. So we do a high-level visualization, and automation improves the safety risk in terms of your pack. So you can see each and every pack that you have, and Huawei has got an optimizer, meaning that this optimizer can actually prevent this battery from stopping this battery to charge, meaning that one pack, if this pack is not working for some reason. The SOH on this is actually 80%. It cannot actually stop these ones from charging to 100%. So we're actually talking about a high precision on the pack level, real-time online. We also talk about low cost, no need for professional to go on site, because on your BMS, you are able to actually control and actually see what is happening. And also on the warning side, we actually do like 7 days warning. So your pack will give you a warning on your BMS for like 7 days to actually start preparing any maintenance that you need to do on the pack that is actually having a problem. No impact on benefits, certain online calibration during ESS operation. So you don't need to stop your ESS on this one. So actually, we do the online calibration. So if ever we find out that there is an imbalance of the SOC, we actually do the online calibration during the ESS operation. And also no safety risk, so that means no external charge is required to avoid battery packs and cable are removed and installed. So on this one, so there's no risk that you actually have because you don't remove anything to do the calibration and stuff, okay? So about to finish now. So safety energy, we're talking about 4 values that we offer. One of the values we actually do is strengthening the specialized fire safety regulation of ESS. We ensure our customers they're actually protected on this in terms of your fire safety, and we also offer a certificate for this. We also drive global harmonization on this one, also on the ESS safety grading standards. We also develop capability, visualize and manage ESS safety across its entire lifestyle. We also do the development of comprehensive, for full process risk of the assessment of the ESS. So we are fully compliant with the fire department when it comes to this, and also fire risk that can actually happen. So the entire battery can actually do, we call it a prime quality and a safety procedures and objectives. So on the prime quality objectives, we can actually offer you non-flammable, non-spreading, and non-explosive and non-harming. On the basic quality, we also offer non-downtime, grid-friendly, because this is a grid-forming inverter that we actually offer you. So grid-forming PCS and ESS, and load-friendly and environmental-friendly. So in terms of your customer demand, we know that customers, they actually require the R&D, design and test, and supply, procurement and manufacturing. All these, they actually, that actually, for customer satisfaction, we actually do this. So we also have a 20 years life cycle in terms of degradation. We actually support you in Huawei with degradation in terms of 20 years in terms of your 0.5 second or 0.25 C. So 0.5 C or 0.25 C, we do 20 years life cycle. Of course, we're talking about, we also have to look at in terms of your cycles, if it's 1 cycle per day or 2 cycles per day. So we can actually able to support you and calculate this life cycle for your battery. At 60%, we are actually guarantee you on these batteries, but anything that is underneath 60%, we cannot actually guarantee you. Okay. I think I'll stop there for today. Thank you so much, Salim. I will open up for Q&A.
Very, thank you, Henry. Before opening up for Q&A, the audience is asking you to also open your camera, to turn on your camera. They did not see you.
I'm trying, right? I'm trying. I don't know why.
Okay.
That video.
All right. So I will jump directly to the question because there have been many questions during your presentation. I will take one question from Patrick. Since we are talking about safety consideration, Patrick is asking, has battery storage deployment increases globally? Safety has become a critical issue. What are the most common causes of fire incidents in energy storage system?
Sorry, what are the most?
What are the most common causes of fire incidents in energy storage system? The most common.
Some of the fire incident which we actually see, we've seen that especially when the PCS is not having the DC-DC. So our PCS has got a DC-DC in terms of blockage of any backfeed current that might come from the grid, because you find out that you put a battery and the battery is actually sitting there probably on the arbitrage or whatever that you actually do your battery backup, whatever that you actually do in a battery. But you find out that if there is a power grid loss, or maybe there's a power grid, weak grid on that side, and then there's a power grid loss, there's something called HVRT or OVRT, over voltage right through. So there's a backfeed current that goes from the grid to the battery. Of course, the current needs to go somewhere. So you'll find out that that current will actually shoot, and it's very high current. Some of the PCSs, they can actually withstand it and actually switch it off. And some of the PCSs, like central PCSs, they cannot switch it off. So you find out that that current will actually go straight to the battery, and which will actually cause issues of heat on the battery packs. And after that will actually cause fire. So those are the fires we've seen on the batteries causes. And also one of the things also is poor insulation in between the cells, because the cells are packed in a way that they can actually parallel in series. So you find out that on those cells, there are no good insulations, and those insulation can actually burn during the fire or during the current that is high, so when the fire starts. So we've seen those issues that is happening, as I've shown you in China, in Korea, in South Africa also. Those are the issues that actually started the fire on those areas. Yes.
Thank you. Just one question for clarification. We have someone here, didn't mention the name, is asking, is it true that CALT is buying Huawei Digital Power products?
Is it true that?
CALT, C-A-T-L, it's also a company, so they are just asking. Huh? CATL. They're asking if CATL also buys your products.
It's true that CATL buys our product.
Yeah, so it's a question asked here. I think it was important for me to
this.
take it just to clarify if maybe, since people might be willing to buy your product. So I think there's something that needs some clarification.
That's a good question. You know, just a little bit of history. CATL is a company that is actually, what does CATL do? CATL, they only manufacture cells. They don't manufacture batteries. They only manufacture cells. So they do the electromechanical of the cell, of the battery. So they only do cells. So all the technology that they have on their battery system or their ESS system, the battery, is actually coming from different suppliers. Of course, not from Huawei, but different suppliers. So they only supply cells on that system. So there is an incident. One of the projects in South Africa is called Hydra. It's in the project is done by Total Energies. That project was won by CATL, but CATL, they were supposed to offer a grid forming system on that. So they found out that the PCS that they were using, of which is a third party, because they don't have a PCS, PCS is someone else. So that PCS that they were using could not actually fulfill all the grid forming capabilities that Total needed and also Eskom needed. So then they called Huawei, because they know that PCS from Huawei, our string PCSs, they can actually do grid forming. So that's how CATL went and buy Huawei PCSs. So that's the only collaboration we actually had with them. So they can provide the battery, we can provide our PCS. So our PCS is a grid forming capability, has got grid forming capabilities on weaker grids, or when there's a low short circuit ratio, probably a circuit ratio of 2 or circuit ratio of probably 1.9 or 2.1. So we are able to offer our PCS in that area for CATL to actually do the collaboration of the two technologies. Thank you.
All right, I think it was very important to address this question, and also apparently the person who asked knows about this situation. Thank you very much, Henry, for this presentation and for clarifying this last question. Now we'll ask you to turn off your microphone as well as your camera so we can take the next speaker.
Thank you.
Welcome. The next speaker of the day is Eustache Ocean. Eustache, you can now turn on and off your camera and mic. Perfect. So Eustache Ocean is the technical director of the EA region from SAG. And I'm heading over to you this presentation, Eustache.
Thank you very much, Salim. I hope I'm audible from the other end.
You are very audible.
Okay. Thank you. Good morning, East Africa. Good morning. That's where Southern and Central Africa. Good afternoon, East Africa. So my name is Eustace Ocheng. Salim has already introduced me, so I'll go directly to introducing the company, SAG. Then we'll delve into the topic today, that's designing resilient energy storage and solar for mini grids. So just to introduce SAG, SAG is a Chinese-based manufacturer. The company was established back in 2005, majorly focusing on industrial automation, later into the renewable energies. And since then, we are handling the two areas, working together to ensure that we can be able to provide better products within the market. We entered into the African market around 2023, and you'll be able to open up in different countries across Africa. That's in the East Africa region, Southern Africa, and also West Africa and North Africa. So just to give you a deep insight on the solutions that we offer as SAG, we are focused majorly on the residential solutions and commercial and industrial. For the residential, we have different kinds of solutions, from the low voltage battery solutions, low voltage hybrid inverters, high voltage hybrid inverters, and also high voltage battery solution, and also in all-in-one solutions also. These are some of the products that we are offering from the range of 3 kilowatt up to 20 kilowatt for the residential space. Also, in the commercial industrial, we also have a variety of solutions that we offer. And this is based on the customer requirement, the customer needs. We have solutions like CHS2, which is majorly common within the Africa region, which is fitting best to our challenges that we are facing, which I'm going to discuss in this presentation too. We also have solutions like CM2. They are solutions that are majorly for the on-grid application, and SL is in the Europe region where the grid is very stable. We also have CHS3, which is just an improvement of CHS2 in terms of the capacity provision. So if CHS2 is a 50, 100 kilowatt hour, CHS3 is a 125 to 61 kilowatt hour. Both those solutions are all in one with hybrid inverters of 50 and 125 respectively. One is air cooled, the other one is liquid cooled. And I think from the discussion that you have had from the previous speakers, you understand what air cooled is and liquid cooled is. The difference comes in terms of the power consumption and also the size of the solution, because as you go larger in terms of the capacity, then the need for cooling goes higher. So that means that it's better to shift now to liquid cooling at these particular levels. We also offer options for low-cost alternatives to the all-in-one. So that means we have the IP20 versions, where you can do the rack-mounted, plus the similar inverters that we are offering in the all-in-one IP55 versions. So these are the range of solutions that we are offering as SAG in the market. And through this discussion, I'll be hinting in some of the features of this particular solution. Now, getting into the topic of today. Just move my screen. Yes. Also, as I started, I mentioned that when the company was established back in 2005, our major product was industrial automation, and that's where we were dealing with the VFD drives. And as you can see, we have a variety of VFD drive depending on the application, from the universal, that's the industrial ones, and also for the water pumping solution, we have the solar pump controllers from the range of 2 kilowatt up to around 400 kilowatts. So it depends on the needs of our customers. And I'd also show you how this solution come handy into our mini grids and ensuring that we are providing resilient designs for our mini grids. So getting into our topic of today, we were trying to discuss about how designing resilient mini grid help a lot in improving cost-effective power systems. And just to give you what is the definition of a solar and a storage mini grid, we are looking at a localized solution that is able to do solar generation and also battery storage for reliable power production, which can be independent or work alongside the main grid. And if we look at resiliency in terms of the mini grid, then we are looking at a system that is capable of supplying power despite the load changes, weather variation, or any fault that emerges from the equipment or from the grid. The system is able to work alongside. So this is what defines what we are discussing today, and we want to look at how are we able to design these resilient mini grids. So first of all, we look at why mini grids matter. So looking at Africa generally, we can see that we still have energy inaccessibility in some areas. Some areas there's stable power, some areas there's weak grids, some areas there's totally no access to a grid. So mini grids matter a lot because they're able to be alternative to this grid unreliability. Most of people are using diesel generators as an option for areas that maybe have weak grids or there's no grid completely. But as you can see, the cost of fuels keep on increasing, especially in this period of time where we're having challenges with the grid with the fuel cost. You can see even the maintenance of the generator is very high. So mini grids with solar and storage comes in as a best alternative. There's also the growing demand of clean energy, and you can see major companies are participating a lot in ensuring that there's clean energy. And recently participated in an event which was hosted by CAM, and you can see major companies are competing over clean energy. So you can see it's easily adopted to the C&I section. Also, mini grids are able to provide resilient energy, and that means going to provide you with stable power, which also improves a lot of business. Now, looking at the challenges that we, Africa, we might be facing majorly when it comes to our grid network. One is the high cost of investment. You find that the grid is there, but the consumption is low. So the cost of maintaining this particular grid is very, very high. There's also efficiency concerns. Of course, there are a lot of blackouts, there are a lot of low voltage triggers within our grid. Scalability is also limited in areas where the population is sparsely populated. So you find that scaling up the grid is very, very difficult. Complex installation and management also comes in handy, and also lack of after-sales support, where you have a transformer that went down 1 month ago and still 2 months counting, it's never replaced. So these are some of the challenges that we are facing a lot within our grid network. And we are looking now at how we can be able to now work on mini grids and design solutions that are resilient. And key thing, if you look at mini grids, we are looking at some of the key components. And the key components are just basic components that all of us know. One of it is the solar panels, which are able to generate power that is directly from the sun. We have the inverters coming in. We have all hybrid inverters, also have grid forming inverters. And I think this is something also the audience should also be able to understand the difference between these hybrid inverters and the grid forming inverters, and how they're able to act along in providing power for the mini grids. We are looking at energy storage solutions. That's the battery storage. And majorly, this is for the backup and also the aspect of peak shaving. And also what is very important is also the EMS, which does a lot of intelligent control that is between sources of power, that is from solar, that's through the inverter, controlling the grid and also the generator, working together to ensure that we provide constant power to our loads. So just looking at a bit of the system architecture, if we're looking of designing any mini grid, You can go with both solution. You can have what we call the DC coupled solution. We can have what is called the AC coupled solution. The best thing for you as engineer or the designer is to find which particular product fits into which design. So if you look at all-in-one solutions, these are systems that comes handy with hybrid inverters and batteries all together. So the hybrid inverter normally is able to take up solar, it's able to take up grid, it's able to take up generator, and work along between the three sources of power to supply power to your load, and also charge at the battery and discharge the battery at the same time. And if you look at AC coupled solution, similarly, it's able to perform the same functionality. The only difference will come that for the AC coupled solution, we have a PV inverter that is typically separate from the base PCS solution. And the control between different sources is done through what we call the static transfer switch, which is able to control the grid, the DG, the PV inverter, the base plus the PCS, and also supplying power to the load. So these are the key differences. All of them will perform as required for both mini grids and also off-grid functionality. So when you look at designing, one key thing that I'll be looking at is redundancy. And this is where you can be able to work with modular systems. As you can see, most technologies, even from the presenters, you can see now most technology is coming from containerized solution into smaller units that can be scaled up for future, and also scaled up for capacity expansion. And having redundancy means that even if one system fails, then it's very easy for you to be able to still run your solution comfortably, because its effect is very little. If you are to do maybe a 2 megawatt hour solution, and you have a 261 kilowatt hour batteries that have been parallel together, you losing 261 kilowatt hour doesn't affect much on your load side, although it reduces your backup time, but doesn't affect much on the operation, compared to having a centralized battery solution where once you lose 2 megawatt hour, then it's gone. You need someone to be able to work on it, to be able to revive its operation. The other thing that when I look at resilient design, look at the backup time that you need, whether it's 3 hours, whether it's 5 hours, you need to consider that. And in considering the backup time, you also need to consider the load prioritization. That means you need to define what a critical load is and what is an uncritical load, because this helps a lot in also reducing the cost of the project generally, because battery is still very expensive. When you look at the whole solar PV structure, system structure, you find battery is the one that still has the highest cost. So defining your critical loads is very important. This helps a lot in also reducing these hours of autonomy, or increase the hours of autonomy for the critical loads, versus having both critical and uncritical load being supplied by the battery. The other thing is flexibility, and that's now come handy of whether you're going to use the hybrid inverter or whether you're going to use the AC coupled solution. Then the other thing is to look at scalability in future. Can you be able to increase the capacity without interfering much on the structure of the system? So these are some of the things that you need to consider when designing a resilient mini grid system. And when you look at the sizing, which I think most of the engineers now are aware of, some of the key things that you need to consider at the peak load is the inverter able to handle my peak load? Because I've seen a lot of designs where when the customer says my load is 10 kilowatts, the best we can do is to give the customer 12 or 15 kilowatts. Yet we are not looking at the peak load, the surges that comes in with the system. So as SHJ, if you look at our CHS2 solution, which is a 5100 kilowatt hour, for most of the customers that are using this solution, you find their base load is around 10 kilowatts. And this 10 kilowatts is able to discharge 100 kilowatt hour in less than maybe 12 hours. But still the inverter is at standard 50. That means the inverter can be able to handle any surges that comes in along the system. So the best thing is to try to design an inverter that can be able to handle surges and peak load comfortably. The other thing is to define critical load, as we have mentioned below. in the previous slide. So for the hybrid inverter that we do have as SHJ, it's able to take both critical load and uncritical loads. So that means that critical load remains on the grid input side where we consider it as an on-grid load. Then the critical load comes in the backup side where it can be able to be supplied by the battery in case there's any power outage or power loss in the system. Then considering the battery, that means you have to consider the load times the backup hours. So that's the critical load times the backup hours that you need. That will help you to design the size of the battery that you need. Also consider that the battery has a depth of discharge. And also the battery has an efficiency. So all these things need to be considered together before you define the size of the battery capacity that you need. Because you find that if it's 10 kilowatts that you need 10 hours, that doesn't mean that 100 kilowatt hour is enough to provide backup for this 10 kilowatt. You need to consider the depth of discharge which you're going to use. For the solution that you have, like the SHJ CHS2, you can do up to 95%. That's the depth of discharge in an off-grid operation. So that means that you need to consider that's 5%. DOD, that's the end of discharge, and also need to consider the efficiency of the system generally. Then if you look at maybe some of the data sheets, this guides a lot, especially now when you're designing for the PV. You find that for the maximum DC voltage is normally, depending on the inverter, like the CHS2 inverter, the maximum is 1,000. So when you're designing for your PV string, that means you need to work with the rated power.
We remain with some time before we take questions, so we will let you finish the last remaining slide quickly.
Okay. Thank you, Salim. Yeah, so I'll skip through. The other thing that I'd mentioned is on the VFD. So you can see there's also aspect of VFD integration. And for SHJ, given that we have a lot of experience in terms of industrial automation, and you can see nowadays that we are trying to do off-grid solutions so that you can be able to run even more inductive loads. So working along with the VFD solutions help a lot into integrating these particular loads as critical loads within our system. Initially, these loads would be considered as non-critical because of the demand surge that it needs, especially when it's starting up. So with our VFD solutions, now we can be able to integrate along with this system to work to provide energy supply. The other thing we consider for the mini grids are the working modes. So we have different types of working modes, which you need to consider, especially when you are in operation. So we have the maximum self-consumption, there's time of use, there's microgrid. So choosing the right working mode helps a lot into optimizing your solution and getting maximum energy from it. The other thing is the monitoring platform. Having the best monitoring platform helps a lot into getting real-time information, having a smart dispatch. Also, the generator automation also comes handy, where you'll be able to know when to bring in your generator and how much your generator will be producing and when your generator should be able to exit the system. At the end of it, we are looking at the system being able to provide stable voltage and frequency to ensure the seamless transition between different loads. Then if you look at now as a conclusion, the benefits and what we can be able to get from a resident design is that what you are aiming at is to reduce the electricity and fuel costs, improve the reliability and uptime, and also because it's solar, then we are also contributing into lower carbon footprint. And the mini grids are essentially modern systems, and we can say mini grids are not designed for the rural areas. Currently, the mini grids are also going for the industrial areas where the C&I ESS applications are coming in. So this tells you that the solar solution mini grids are coming in for the modern operations, and you can see some of the cases that as SHJ we are able to do across the continent. You can see we have commercial buildings. We are looking at a chicken farm, petrol station. We are looking at the billboards. We are looking at hospitals. All these are able to work in isolation where there's no grid, and also can be able to work alongside the grid. So that marks the end of my presentation. I welcome questions. Thank you very much, Salim.
Thank you very much, Eustace. And apparently, you just have a question from your fellow speaker. I will let Henry. Do you have a question?
No, I just said I managed to fix my camera. I'm sorry. This is me, guys. Sorry. Thank you.
You're welcome. Thank you very much. It's fine. So, Eustace, since we don't have a lot of time, because there is a lot of interesting questions addressed to you. As you have seen, we have moved from CNI, large scale, and then we transitioned to mini grid. Many people were really interested to learn a little bit, but I'm going to take one question before we move to the next session. The question from Henry, but not Henry the speaker, another Henry from Zimbabwe, is asking, how can developer ensure long-term sustainability and operational reliability of mini-grid in remote or harsh environments?
Okay, that's a very good question, Salim. To ensure sustainability for mini grid, especially in the remote environment, first of all, is to have a simplified solution. And I think all-in-one solutions are the best because they come already pre-integrated. There's not much to be done. Number two is that the system should be able to provide a longer warranty term. That's for the parts replacement, and ensure also the parts are available. And if you are doing any size of a project, try to calculate if you can be able to stock some parts, you as the customer, or you can check whether the manufacturer has parts maybe that are reachable within the country. So that's ensure a lot of peace of mind when it comes to sustainable solution within the rural areas.
All right, last more question. What are the main faults associated with base integration to an operational solar PV plant?
Come again? Sorry.
What are the main faults associated with base integration to an operational solar PV plant?
Okay, the major faults in terms of technical faults, you'll find that majorly they emanate from the DC side. And on the DC side, there's the consideration of the PV input capacity in terms of the voltage. So designing the right length of strings and also distributing.
Hello, Eustache, are you with us? Apparently, we lost Eustache. Then I will have to move to our last speaker of the day. So, Eustache, if you are not with us, I will request Bertus to turn on his camera and his microphone. Perfect. Perfect. So, okay, perfect. Bertus is the CNI Technical Engineering from SunSync. With Bertus, we discuss about scalable energy storage system technology for Africa. Bertus, we can see you, and please speak so that we can also ensure we can hear you. Thank you. You are not audible, Bertus. We can see you, we can see the screen, but we cannot hear you. Can you speak, Bertus? Or it is a microphone on your side? Currently, we have a technical issue. Allow us to check internet audio.
Hello.
Now
You
it's
know?
fine. Now we can hear you, we can see you, and I will ask you to share your presentation so that,
Right.
yes.
Okay.
Perfect, perfect.
Yeah.
As I was saying, Bertus is our last speaker of the day, and he's going to deliver an amazing presentation on scalable energy storage system technology for Africa. Bertus, I can confirm and attest that everything is fine for you to start.
Thank you. Good afternoon to everyone. Very big thank you for joining us. I would like to thank Salim and them for putting up such a cool seminar this afternoon. It's very encouraging seeing what everyone's up to, technological advancements, and yeah, without further ado, I'm Bertus van der Merwe. I'm with Sunsync, based out here in South Africa, with a keen focus on expanding into some of the African markets. Before I get into my presentation, being that I'm the last speaker of the day, I thought I'd just leave everyone with a thought, given that we are all in the solar industry. I think sometimes we wonder why we are. So in late 2024, some combined sources estimated that the current annual global consumption of electricity sits around about 300 million gigawatt hours per year. A few years ago, NASA published a estimate that in any one given hour on a peak in the peak daytime, we intercept around about 174 million gigawatt hours worth of energy within that 1 hour. It's quite encouraging to think about that statistic when you think about the developing countries on our African continent and the scramble to set up energy security for all of these economies. Now, with such a rich abundance of energy, it becomes less about harvesting this energy and more about how we can safely store it, control it, and dispatch it exactly at the moment that demand calls for in industry. Mines, cold storage facilities, data centers, they don't just operate when the radiance curve is high. The energy demand is 24/7. So Sunsync is a new entrant into the CNI space. Most people would know us for our ventures into the residential space over the past few years, but we are definitely excited to hit the ground running and join everyone that has been doing so well the past few years. Sorry.
Is everything fine on your
Sorry,
side?
I'm just experiencing a bit of difficulties, yeah.
I can help you by sharing it on my side if you want.
Yeah, sorry, Salim, if you wouldn't mind helping.
Okay. So can you stop sharing so that I will do it from my hand? Okay. Please direct me.
Perfect. Yeah, we can jump to the second slide.
Here
Okay.
we are.
Thank you so much. Right. So as anything evolves in life, the energy storage question has changed over the past few years. We believe that something from whether or not battery is even a essential infrastructure to integrated large-scale solar. More than that, where the question has kind of shifted from do we need a 2 hour, do we need a 4 hour backup system to something a lot more nuanced. Before I move any further, Salim, if you wouldn't mind just jumping to the next slide. Just a few more statistics here. Recent World Bank enterprise surveys indicate that sub-Saharan African countries still experience around about 7.6 outages per month at average duration of 1.9 hours per outage, and that accumulates to around about 14 hours of disrupted power exposure on a monthly basis. Now, for large energy off-takers, this has become very high operational risks and continue to do so. As this energy question shifts in the African market from whether or not storage is viable and what is the size of backup or the amount of megawatt or kilowatt hours that we need, storage has increasingly become standardized as operating requirements for businesses, productivity requirements, and competitive requirements, without which they cannot function and cannot grow. Our hosts, AFSIA, have also recently published their project tracking at around about 31.8 gigawatt hours worth of storage projects under development currently across Africa. Now, with this question shifting, we at Sunsync believe that the question is no longer whether storage matters at all, but the question becomes what kind of energy storage system actually deserves to be deployed, financed, and trusted at scale with these large energy storage systems. Right, we can jump to the next slide, please. And the next one, please. So our approach at Sunsync in terms of designing bankable C&I large-scale storage solutions, in particular for the African market, has been based around three core principles. Firstly, we looked at the challenges and the requirements in staring us in the face that at these large scales, at multi-megawatt projects, data sheet duty cycles or nameplate numbers don't really matter out in the field. So having a proven system that can actually deal with real world duty cycles. What I mean by duty cycles, when and how the battery discharges, how it charges, how it decides to hold in reserve, and how it's exposed to site conditions on a daily basis. Then secondly, we always take into account architecture. We believe that the winning system in the African context will be a system that under one umbrella integrates efficiently battery, PCS, EMS, safety and thermal control without having multiple points of procurement, multiple points of interaction with multiple OEMs and or partners. Lastly, we look at the application, what it actually means for African deployment support at scale, how the product that we've recently launched into the market, what it would mean to OEMs, EPCs, IPP developers, project owners, and large-scale energy users deploying this solar, not just in South Africa, but across the continent, and how we aim to support this function at scale. We can jump to the next slide. Thanks, Salim. And the next one. So real-world duty cycles. Today's modern energy storage systems have to support a lot of functionality, control strategies, not just store power. A lot of the speakers this afternoon have told you about peak shaving, PV self-consumption, time shifting of solar energy, in some instances, the ride through during the outages, diesel displacement, generator integration and coordination, islanding capability that you need to take into account when designing a large-scale ESS, grid forming, ramp rate control, capacity support. And as the rules evolve, with some of the markets adopting exportation to the grid, all of these energy systems need to take that into account on a daily basis. Salim, the next slide, please. Fundamentally, all of these control strategies I just mentioned are differing problems. And in essence, a demand management or a peak shaving application is not the same as a backup or a resilience application. A backup and resilience application is not the same as a renewable firming or a grid support application. And none of these are the same as baseload displacement, diesel displacement, and dispatchable supply applications. The next slide, please, Salim. And this is where we believe that most energy systems or energy storage systems start to actually fail, not because the battery or the cells are inherently of a poor quality, but because in some instances, OEMs fail to recognize the use cases, the strategies, and understand them precise enough to adapt the architecture of their system in accordance with these real world applications and the strain that you're going to be putting on the system for years to come. Now, some common, Salim, you can go to the next slide. Some common things that might seem to everyone as baseline designing of some, not even a large-scale system, but you'd be surprised how often you encounter energy storage systems where the PCS is not large enough and the system ultimately misses the peak. Batteries are not scaled or scoped large enough. You run out of energy before the tariff window closes. Controls are sometimes very simplistic when we talk about EMS, and that burns cycles at the wrong times. One of the previous speakers quickly touched on the thermal design. If the thermal design is weak, performance completely derates when the site needs it the most. And when your operating window doesn't really match warranty assumptions, or your warranty assumptions do not account for very harsh environments like the African environment offers us, the business case completely starts failing before even the battery does. Salim, we can move to the next slide. So we at Sunsync believe that just as the battery, now you can stay on that slide, thanks, Salim. So just as the battery chemistry conversation has changed over the last few years and LFP has no longer become a headline, but sort of become the baseline. The reason being that it offered the stationary storage industry exactly what it needed. Needed lower cost, stronger life cycles, greater reliability in terms of thermal stability, and a safer profile in terms of long duration for stationary assets. We believe that what will shape the competitive landscape in the years to come when we talk about large-scale energy storage systems doesn't necessarily happen at the cellular or molecular level when we're talking about LFP batteries, but what each OEM decides to do and innovate everything around that battery to get that LFP platform to perform reliably under heat, effectively cycling for years to come, account for grid instability, generator integration, remote service conditions like a lot of African sites do, and evolving commercial use cases. Okay, we can go to the next slide. Thanks, Salim. That brings me to the second theme in terms of architecture and why we believe that architecture ultimately wins this newfound race in terms of large-scale energy storage systems. Is that energy that is stored is of no value to any of us completely on its own, but the configuration of effective systems that dispatch that energy as and when required at a high rate of efficiency, that is what makes a system bankable at the end of the day. And it is only achieved through taking all of the layers of the architecture into consideration, some tangible in terms of the system and some ancillary, let's call it unique selling points. We can go to the next slide. Thanks, Salim. Firstly, when designing a bankable CNI large-scale system, obviously you're going to look at the electrochemical layer, that base layer of cell format, voltage window, depth of discharge strategy, thermal range, cycling profiles, and degradation assumptions. A lot of developers and or financiers have sort of standardized in terms of minimum capabilities of energy storage systems already. However, the next layer on top of that, we believe, is the power block and the packaging of the entire system. Increasingly, we observe the industry moving towards higher rates of full system integration, more modular prefabrication, more factory integrated architecture, wiring, protection, dispatching a all-in-one solution that is completely turnkey by the time it hits site. There's fewer critical connections left to be solved during the commissioning phase. There's smarter thermal control. Our units, for example, have not just the capability of controlling the temperature inside of our all-in-one units, but also factors such as dehumidification, cleaner augmentation paths, and more maintainable package design that in the long run can effectively be maintained in a very, very remote site. Why is this all happening? Because every avoidable field interface is currently creating risk on large scale ESSs. Every unnecessary connection adds to commissioning complexity for dispatching EPCs. Every unclear boundary between installer, EPC, the end user, or the developer creates responsibility gaps that we believe that all-in-one systems completely solve. And poorly integrated auxiliary systems become future availability problems. And lastly, the third layer, we talk about EMS. As I go through Sunsync's offering, you'd note that we placed a lot of emphasis in terms of the development of our own EMS and its ability to dispatch intelligently energy throughout the system from multiple incoming and exporting sources. Very high levels of anomaly detection, states of charge, states of health, the monitoring of remote diagnostics, and ultimately being warranty aware in its operations. Salim, we can go to the next one. last point I'll quickly touch on is the application and what it actually means for the African environment. And at Sunsync, we believe that African energy storage projects or infrastructure needs to be selected as long-term infrastructure. These are assets that are going to take a hammering in very harsh environments, and we believe that consolidating everything into one offset point, one OEM, will ultimately be the difference between whether or not it's a good system and whether or not it's a great system. We can go to the next slide. Thanks, Salim. So real operating conditions, there was a question that popped up in one of the Q&As. We've taken a lot of time before launching our CNI solutions to ensure that at high ambient temperatures and high percentages of humidity over a long period of time, the system would not begin to degrade. Unstable grid supplies are managed through oversizing certain components in our systems so that we can dispatch and be sure that it can sustain the demanding environment that the African continent can throw at it. Generator integration and complexity. Again, one of the previous speakers had a question about generator integration on mines. It is a reality that we cannot get away from, and your architecture and deployment in the African market needs to account for this. Remote locations and very limited specialist support. In terms of Sunsync's approach, you'll see a little bit later, our plans to scale our CNI rollout will enable us to offer on-site specialist support anywhere within Africa. Changing load profiles, we need scalability within some of these systems, putting down one solution and thinking that you're going to solve all of your problems. It keeps on changing on an annual basis. We can go to the next slide. Thanks, Salim. So we believe that these systems need to be, especially on large-scale energy storage systems, they need to be integrated enough to reduce project risk, but again, modular enough to scale in the future, integrated enough to simplify deployment, but modular enough to maintain and replace components as and when required. Integrated enough to create one clear responsibility boundary, but modular enough to support future expansion without architectural regret or design regret. So, like I said in the beginning, the energy storage system question in Africa, we believe, is changing. It's been changing for a while. We believe the better question to start asking is, can the system that you base your future CNI site off, can the system actually be deployed, operated, monitored, expanded, serviced, and trusted under the actual conditions of these sites? We're going to the last slide. Thanks, Salim. So introducing Sunsync's LK modular range. Again, I've touched on a few considerations that our engineers at a global level took in developing these solutions, and these solutions are use case led variants. Anyone that contacts Sunsync for design consultation would see that across our LK range, we talk about these variants. We call these variants on-grid with MPPT, hybrid with MPPT, hybrid plus auxiliary, and then full hybrid. Whilst the slide is very deceiving in terms of all the use cases, control strategies and considerations that were taken in including the components that are required to effectively deliver a use case led variant to the market is not all encompassing in what you see in the slide. What we try and solve with our on-grid units is typically arbitrage and peak shaving. On-grid with MPPT units, we try and solve all of the above listed, plus add the ability to have PV self-consumption. In terms of hybrid solutions, this is where we start looking at larger scale backup, grid instability solutions, hybrid plus MPPT, PV backed reliance, all of the above again. And just for out of interest sake to mention to everyone, all of our hybrid solutions, as soon as we start moving over into the hybrids or integrated with very high performing static transfer switches, as well as a galvanic isolation transformer pre-built into all of these variants as a standard. Secondly, modular architecture, add what you need to the project. If you're going to scale the project, there is cabinetized space in order for you to expand only what you need in future. You do not need to buy an additional cabinet and additional unit to expand your system in the future. Lastly, deployment support. I touched on this a little bit beforehand. Currently, we encourage anyone looking at dispatching a large-scale energy solution across the African continent to contact Sunsync. You can get in contact directly with us for design consultation, configuration guidance, some schooling in terms of these new products that we've launched, what they include, what they don't include, a little bit more detail in terms of the architecture, the data sheets, commissioning assistance. As I mentioned before, we are scaling our commissioning assistance. So with each and every unit sold, as we scale our sales, we are offering direct OEM commissioning on site, not just remotely. Whilst we offer the remote monitoring service like we do within the residential space, we are also accommodating on-site service capability in terms of removal, replacement, and repair of modules during the course of a repair and maintenance claim and/or warranty claim. Then, as we move into some of these sub-Saharan African countries, we are dispatching spares and parts into these countries to ensure that we ultimately can service any client that effectively puts down one of our units in a very remote site. So if you buy one of these tomorrow and install it in Angola, rest assured that we will be sure that we can supply you with spares and/or parts to ensure that your system can keep on going. Then lastly, local and global engineering support. Again, as we scale, we're not just scaling in terms of training, capability to assist you and service you with repairs and maintenance on site, but we're also growing our local support team in order to ensure that you can reach us at any point in time should you have troubles with your system. Thank you so much. That's it for me.
Perfect. And I think this is the time to take some last question. And I hope I stop sharing my screen as well. So moving to the question before we close the session, we have a question here. Is Sunsync an OEM or does it use third-party OEMs?
So just like everyone else, We're not a battery cell manufacturer. We have inputs in terms of the architecture that goes into our PCSs, not so much our STSs and transformers. There are guys that do that a lot better than what we could ever dream of doing. I think the party trick with us is and always will be taking key components and designing a system that works. And specifically when it comes to the EMS, it's our proprietary coding architecture that ultimately dispatches energy throughout the entire system and makes it work so well. So I hope that answers the question.
All right, and one last question from Henry, asking is saying designing bankable CNI and large scale storage system. Okay, let me read. So he's asking what are the policy, regulation, and market changes are still needed to accelerate large scale ESS adoption across the continent.
Sorry, I just want to see if I can read it. I didn't hear everything you said.
I'm saying we have a question here from the audience asking, what are the policy, regulation, or market changes are still needed to accelerate large-scale ESS adoption across the continent?
Look, there's a few case studies, obviously out of some large mines and some active IPP developers currently across the continent, where you're talking about 20, 30 megawatt plants going up. So I think from a private sector point of view, the wheels are turning already. I know that Kenya, for example, 2 years ago, started playing with the idea of exportation of or allowing the exportation of energy through both residential and CNI off-takers into the grid to help and create a better energy mix within the country. I think it's a mixture between the two. It's not necessarily a policy thing. We've seen very slow-moving policy in South Africa relative to the rest of the world. I think the African market is not going to be any different. I think it's going to be a very slow uptake in terms of regulation changes and things that would accelerate it. I would be more excited about what some of the developers and the IPPs are currently doing in the African market. And based on that, the rate of CNI adoption in the last few years have just been amazing. I think Safia, actually, you guys quoted in the pamphlet to this seminar that the African continent, in terms of CNI and specifically large-scale energy storage systems, have experienced compounded growth year on year, not percentage points. So I think it's not as easy as just saying I think that is going to be the thing that changes it. It's a multitude of factors.
And this also bring me just to my last notes before closing this session, because if you can also allow me to thank all the speakers of the day for the amazing presentation. And if some of them that are still here with us, I will request them just to turn on the camera so that we can see them. And just to touch base on the points that you just raised, it's very interesting because we have a dedicated session where we will address all those concerns, just to also help me present what the audience should expect tomorrow. As you can see here, today we had this discussion. Tomorrow we will be mainly discussing about project and financing. And this is just to share with you a lineup of speakers that we will have tomorrow. But to touch base on what Bertus, you are saying, we have a dedicated session where we will have grid operator, developer, and OEM to address such kind of question. But also on the last day of the conference, we will have a pure session with regulatory institution to discuss about regulation and policy landscape. You just mentioned about what Kenya did, and the good thing is we will also have the regulatory institution of Kenya present with us for this session. To close today's session, I thank everybody who joined us, as well as all the speakers for delivering this amazing presentation, as well as our sponsors. Thank you once again. I invite you to join us again tomorrow because it will be more of project and financing, and we have a very great lineup of speakers. I will let the session for 1 minute until we just but let you guys put some last question that we'll share with the speakers. Thank you very much.